Homework 15, Exponential Functions, Video 4, Graphing Part 2. I meant to go ahead and set up a table and an empty graph like I had at the beginning of the previous video, but we've already started the video, so I'll just throw it up really quickly. So this is almost exactly like the previous problem. Graph this exponential function, fill out this table, connect the dots. And in your homework, there are some problems where you have to complete a table. But there's something different about this one, and I think it's pretty obvious. It's that this base is a fraction. And my apologies, in the previous videos, I neglected to mention that this part is called the base, and this part is called the exponent. So our base on this one is 1/2. Now, because it's a fraction, will that change anything? Well, yes and no. We're not really going to do anything different. The outcome's going to be just a little bit different. And it's not necessarily because it's a fraction, but because of how big the fraction is. So let's look into the table of values by substituting 3 through -3 and see what happens. Don't let the fraction intimidate you. Fractions are not that bad. They have a bad rap. If you do 1/2 to the 3rd power, that just means 1/2 times itself 3 times. Well, on the top you would do 1 times 1 times 1, which is 1. But on the bottom you would do 2 times 2 times 2, which is 8. So 3 to the 2... 1/2 to the 3rd power is 1/8. So we go over 3 and barely up, which was a complete contrast from the previous one when we were way up there. If we put in 2 for the exponent, we get 1/2 to the 2nd power. That's just 1/2 times 1/2, which is 1/4. And already some of you are starting to see, wait a second, I see what you're doing. If you think you see what I'm doing, I invite you to pause and calculate the rest of the points and then connect the dots. Have fun down here, but if you're good at picking up on patterns, you're going to be okay. For those who didn't pause, let's go ahead and finish it. An exponent of 1 is easy. Anything to the 1st power is itself. 1/2 to the 1st power is 1/2. So we have a point over 1 up 1/2. 0 is easy because anything to the 0 power is 1. Except 0 to the 0 power. So when we put in 0, we get a value of 1. Y'all see what's happening here? We're kind of getting the same graph, but it's oriented differently. And when you get to the negative exponents, don't panic. It looks intimidating at first. And I know what the rule for negative exponents is, even though I erased the exponent rules a moment ago. The rule for negative exponents was you do 1 over the positive power. But that looks worse than before, because now we have a fraction inside of a fraction. But really the key thing to listen to are the words and not what I write down. When I said you do a negative power, I said it was the reciprocal of the positive power. A negative power is a reciprocal of a positive power. So this negative power is a reciprocal of a positive power. Well, what's the reciprocal of 1/2? 2/1. But whoever calls it that, just call it 2. So you can change a negative power to a positive power, you just have to reciprocate. 2 to the 1st power is 2. And along the same lines, 1/2 to the -2 power is the same as 2 to the positive 2 power, which is 4. And 1/2 to the -3 power is the same as 2 to the positive 3 power, which is 8. We're getting the exact same answers we got before. We're just getting them in reverse order. -1, 2. -2, 4, -4, 8. Excuse me, -3, 8. So we get the same graph we got before, but this time it starts high on the left and plummets downward. And once it crosses the y-axis, it starts asymptotically approaching the x-axis, and that is a word, asymptotically. It means to behave like an asymptote. Oops, accidentally crossed it, not supposed to, but we'll just chalk that up to sloppy drawing. Yeah. In case you're wondering, it's about 5:30. I've been here for a while. So we get kind of the same phenomenon as we had, except the complete reverse. So let's list some of the things that we listed before. For example, this has a y-intercept at 0, 1, just like it did before. There is no x-intercept because there is a horizontal asymptote at y equals 0. And again, it's only on the right half, so it's a half asymptote. I'm trying to remember the other things we said. This is decreasing, meaning if we were to think of this as a roller coaster being ridden from left to right, your y values would be getting lower. And the domain and range. This graph still goes forever left and right, which means its domain is negative infinity to infinity, but the range, highest to lowest, the highest this graph goes is infinity, so to speak, and because of the horizontal asymptote, this graph will get closer and closer to 0 without ever getting there, so the range starts at 0 but doesn't include 0 and goes upwards forever. So what about this caused it to be the exact same graph except decreasing instead of increasing? And the answer is it has to do with the base. And it's not because the base is a fraction. There are fractions whose graphs would be increasing. It's because of the size of the base. In general, if your base is greater than 1, then the function f of x equals b to the x is the one that's increasing. This is called exponential growth. And if your base is between 0 and 1, so it's positive but it's less than 1, then your function f of x equals b to the x is the one that starts high and gets low. This is called exponential decay. There are natural phenomena that demonstrate this. The one you may be familiar with is the value of your car after you buy it. What happens when you drive it off the lot? The value plummets. Will the value ever hit 0? Not really, because it has some scrap value. I learned that earlier this semester. But anything that depreciates or decreases like this is said to decay exponentially. Another example is radioactive elements, radioactivity in an element. Radioactivity of an element decreases exponentially, so it drops real fast early on and then it slows down, but there's always some radioactive element there. If you're familiar with carbon dating to see how old bones are, carbon decays like this, so if a paleontologist can measure how much carbon was probably in a bone based on its size and measure how much carbon it has now, they can actually figure out about how old that bone is. So just keep in mind that if you're graphing an exponential function and the base is bigger than 1, then the graph is going to demonstrate growth. But if you're graphing an exponential function and the base is less than 1, such as 1/2, then you're going to get what's called exponential decay. But they all have these features. In the next video, we'll talk about taking advantage of graphing functions based on knowing that they're growth or decay and by moving them around some.